This is a warm-up for the unit on roots and radical expressions. We're warming up with a review of properties of exponents. We're going to do a few of the rules, and then we're going to do a few examples. As for the rules, while you could see this typed out or written out or presented to you, just because you're reading it doesn't mean you understand what it's asking you to do. What this is saying is if you have a common base, the common base of A could be X, A could be the number 2, A could be lots of things, and it's being raised to certain powers, the M power, the N power. Well, the rule tells us that when we have this circumstance, it becomes A to the sum of M and N, meaning you will add the exponents together. For example, x to the second times x to the third will equal x to the fifth. You just add them right away. You don't usually leave it as x to the 2 plus 3 power, right? So you actually get 5. But it also works with something like 2 to the third power times 2 to the q power. Well, we can make that 2 to the 3 plus q power. You still apply the rule all the same. Next, when you have a base raised to a power and then that whole quantity is being raised to another power, the rule is to multiply those two exponents. They don't normally write the little product dot over there, but that's what you're being asked to do. So that's what the rule states when you read something like that. What will that look like? X to the second, then to the third is x to the sixth. You've really been doing this since probably 8th grade, if not earlier. So you should actually have a really good understanding of this, and if you constantly have to look over your notes every time you do this, you're not retaining it, you're not learning it. So just make sure you really practice and own the material, okay? Even here, for example, 2 to the third to the second is equal to 2 to the sixth, which you could even take further and make 64. All the same. Next example is A, B to the N power. All you do in this case is you have to keep in mind that on the inside right here, if there's nothing written, those are ones, okay? And you're still going to raise the power, they just each get it. So it's A to the N times B to the N. If you can multiply those two things, sure, you could do that first, you get the same answer. Here I have a B times A to the negative N. There are no parentheses around B and A, so that means that the exponent negative N is only on the A. When you have a negative exponent, you have to know that that means that entire expression is going to relocate. So I'm going to move it from the numerator to the denominator. And that is our new expression. The B, whatever the coefficient is, does not go with it. In this next example, we have it in the denominator and the B is still on top. Maybe the B is on bottom, it would stay on bottom. So here we have a negative exponent right there. Usually your directions will say, no negative exponents. So you have to write everything with a positive exponent. So you'd be done right there. Okay. Next, we have a fraction, rational expression here, raised to a power. The power just applies to the numerator and the denominator separately. Here we could really go about doing it the same way for this other example, but this time I have a negative exponent, so you could look at it as A to the negative N over B to the negative N. So another way I kind of compare and talk about this example, let's kind of zoom in a little bit. Okay, another way I talk about this example is imagine this is the person and this is how they feel about what floor they live on. This person A has a negative feeling about living on the second floor, the upstairs, and B also has a negative feeling about living on the bottom floor of the house. So guess what? They're going to swap apartments. So B is up here. Now it has a positive feeling. It likes this apartment much better, and A is going to go right there, and it has a positive feeling. So if you have to make up a little story for yourself, go for it. A to the M over A to the N. I know it kind of looks simplified. It looks like, oh, that's okay. I mean, all positive exponents. But what do we do to simplify? Multiplication You add, division, we can subtract. Now, I like to kind of put a little disclaimer here. I like to look at it this way when m is greater than n. However, let's say, in this case, let's pretend that m is less than n. Well, in that case, it'll go to the bottom, and n minus m is the winning exponent. So I look at it as a bit of a tug of war. Whoever has the bigger power, that one wins. So if the top power is bigger, it ends up on top. If the bottom power is bigger, top smaller, the bottom wins the tug of war. And the exponent, the whole term, goes down to that side. And then a to the 0 is equal to 1. That bothers some people. They want it to be 0. They don't understand why. Just a quick example to kind of tie in why it is that. For example, if I gave you something like x to the third over x to the third. Well, you might look at this at first and say, okay, anything over itself equals 1. Yay, I'm done. 1. Well, what if I did this rule? I would get x to the tug of war. I guess it doesn't matter who wins. 3 minus 3 on top, say. Well, that equals x to the 0, because anything minus itself is 0. But we just said that that expression equals 1. Therefore, something to the 0 power has to equal 1. Quick little bit of a proof there. These dudes have stars because there's a little extra information. These rules will apply except when, in these examples right here, when a equals 0. They don't apply in that case, okay? For one thing, you're not allowed to divide by 0. Oh, I don't know if you could see that all the way. Well, you're not allowed to divide by 0, and another thing is 0 to the 0, okay? That's the whole topic in itself. That's not going to be equal to 1. We'll talk about that later, okay? Continuing, we have a few examples on bottom. Move this a little bit. I have a few examples down here just to kind of get us warmed up. So you should be able to complete these with just those rules, all right? When you're doing these examples, instead of looking them up online or asking somebody how to do them or waiting for your teacher to go over them with you, definitely just try your best to use rules that are presented to you and make a connection to figure out what the answer is, okay? Got it? Do not give up on it. Do not think you can't do it, okay, please? So if you have to pause, you want to try them first in pencil, go for it, but don't make stuff up either. Sometimes I feel like students, you guys make stuff up and you completely convince yourself that it's good enough because you just want to get something on your paper. If you feel yourself making something up, restart, okay? All over again. Here I just have 2/3 times 6. Again, if you want to try these on your own, press pause right now and come back later. 2/3 times 6 I could just do. There's no powers out here that need to get taken care of first. Some of you guys get weird when you multiply with fractions. Just remember, multiplication could be replaced with the word of. What is 2/3 of 6? Well, 1/3 of 6 is 2. 2/3 of 6 is 4. So that part is going to give me 4. Then I have x to the 7th, which really means 7 x's going across being multiplied. And that means 4 x's going across. Or I could use my rule from up top that basically tells me I need to add my exponents. Done. Here, 4th power for everybody. 4 to the 4th power. 4 times 4 times 4 times 4. Really, you should have a pretty good idea of this by heart. We multiply our exponents in this case, so that is x to the 2nd, and that is y to the 12th. Done. Next example, negative 3rd power. Well, the 3 is really to the 1st. So if I give this power to everybody, I'm going to multiply all my exponents, including the 3 to the 1st's exponent. If I give them all the power, it's not negative 27 over here, okay? It's 3 to the negative 3rd power. We're going to deal with that in a second. X to the 6th power and y to the negative 9th power. Next, relocating with their apartments over here. Don't like it, don't like it. Want to move downstairs. X to the 6th stays upstairs. 3 to the 3rd goes to the bottom, and so does y to the 9th. Bottom, also known as denominator, sure. X to the 6th over 27, y to the 9th. So in conclusion, okay, 3 to the negative third is not negative 27, but rather it is 1 over 27. It's really like a decay. It gets smaller, but it doesn't ever become 0. Another way you could do this is you can make it 1 over those things right from the start. 1 over 3x to the negative second, y to the third, all to the positive third. So you take that whole quantity and move it down. From there, now we give the power, and the 1 stays on top, and we're going to get 3 to the third, which is 27, x to the negative 6th, and y to the 9th, and then x is going to relocate and go up, and you'll still get the same answer. More than one way to do things. Okay. Next example. Squared. I'm squaring each thing over here. I'm going to try to do this as efficiently as possible. I'm even going to kind of skip a few steps, okay? 16 squared, we did that really just a minute ago. It's 256 because 4 squared is 16 and squared again is same as 4th power. X to the negative 5th will become x to the negative 10th, which will go on bottom. So I'm going to end up with an x to the 10th down here. Okay? I'm going to write that down over here. Y to the 20th, that's going to go up here. 13 squared. You square your top and bottom, numerator and denominator. 13 squared is 169. X to the negative 8th squared. Multiply your powers. You don't square it, you multiply them. So it's x to the negative 16th, but I'm going to move that up, and it's going to become x to the positive 16th. And that'll be y to the negative 6th, which is going to go up here as well, and now it's y to the 6th. A little bit of cleaning up. I promise these don't reduce. If these don't reduce, 16 and 13, these are probably not going to reduce, okay? So 250, I mean, think about what's happening. You just have 2 of these and 2 of these, so they can't really reduce. X to the 16th and x to the 10th. So I have x to the 6th. I have y to the 26th. Keep in mind, I reduced. I crossed out 10 x's from top and bottom. I was left with 6. And these, I had 20 y's, I have 6 y's, that's 26 y's being multiplied, all over 169. So these are all examples for our notes or to warm us up, okay? Here, really doesn't matter. Anything to the 0 power is 1, and we're done. All right, next thing. Just a few quick definitions. Root. A root represents the solution to an equation, okay? A radical is a symbol that means root of, and the length of the horizontal bar is important. If you notice, when you have that bar, but you can make it really, really long and cover a whole lot of things. You can make it a little shorter and just cover one thing. It matters. If it's not under the roof of that little radical sign, that's it. It's not, you're not taking the root of it. You're not finding that solution. Radicand is the name of the expression under the radical that you are finding the root of. We want to use all the right words here, okay? Index, sometimes called the degree. It's the number of times the root is the answer, must be multiplied by itself. I had whited out because I didn't like how sloppy my O was before, sorry, to produce a radicand or a factor of the radicand, because we'll be able to simplify stuff. If the index is even, if you're taking an even root, answers must be positive. And if you're taking an odd root, and also if you take it yourself, when you take it yourself, example, x squared equals 4, that means that x equals the square root, invisible 2, of 4. You have to write plus minus. But if the root was already there, you don't have to. All right, if you get confused on that, please just come back and look at this again. It's only when you're the one responsible for taking the root. If the root was already typed or written, you don't stick a plus minus in front, okay? Odd answers can be positive or negative. Oh, must be 0 or positive, actually, because it could be 0. Answers can be positive, negative, or 0. Got it? All things, and you'll only have one answer always. Like if you take the cube root of 8, the answer is 2, but the cube root of negative 8 is negative 2. You can't go throwing around plus minuses when you have odd roots. Okay? Here, what are all the real cube roots of? So, asked to find cube roots. We have a decimal. When you have a decimal for a cube root, please, 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 I'm begging you, write it as a fraction first. So it's 8 tenths, hundredths, thousandths, 8 over 1,000. And we're looking for its cube root. We had to write it ourselves, but it's a cube root. We only get one answer. That gives me cube root of 8 is 2. Cube root of 1,000 is 10. 2 over 10 is 1/5. Done. Here, no decimal, no big deal. Negative 1,000. What number times itself 3 times is going to equal negative 1,000? Answer, negative 10. How about here, if I go to take the cube root of 1 over 27? Cube root of 1 is 1. Cube root of 27, 3. Done. What are all the real, again, we're saying real here, not all the roots, but the real roots. What are all the real fourth roots of? What number times itself 4 times? 4 times is 1. I'm taking the fourth root myself. It's an even root, plus minus. Answer, plus minus 1. Here, fourth root of, even if I changed it to a fraction, 1 over tenths, really negative, hundredths, thousandths, 10 thousandths. Now, while this is great, I would be so proud of you for changing it to a fraction. I'd also think you're being silly because no number times itself an even number of times, 4 times, can possibly be negative. So your answer is no real solution. Here, fourth root, taking it ourselves, plus minus out front. What times itself 4 times is 16? 2. What times itself 4 times is 81? 3. If you don't know these quickly, I definitely suggest making flashcards. All right, study them, know them. What is each real number root? I'm going to move a little quicker now. The roots are written, no plus minus. What times itself 3 times is negative 8? Negative 2. Change it to a fraction. 4 over 1,000. It's a square root. Take the square root of each thing. 2 over 10. Again, that equals 1/5. No real solution. Can't have a negative number underneath a radical when the index, oh boy, the paper's moving, sorry. When the index is even. Negative 2 squared. A lot of times people see a square and square root, like boom, boom, cross them out. That doesn't work here. You have to go negative 2 squared is 4, and the square root of 4 is 2. It's a tricky situation for some people, so be careful there. The reality is, anytime you take an even root, so right here, let's grab another color. You should be able to put absolute value bars on it and be fine. So here, if I did get negative, you'd have to put absolute value bars. I wouldn't write them right now because they're already positive, so it's redundant, but it is the reality of it, okay? Because you won't get negative answers for even roots ever. What number times itself 3 times is negative 27. It's negative 3. What times itself 4 times is negative? Guess what? No real solution. Can't be negative. Again here, negative 7 squared is 49, and the square root of 49 is 7. Absolute value would have to be able to work there. And then here, as soon as you see a negative, that's not a 1 root, that's a square root. It's classic square root. No real solution again. We have a few more examples to work on. Simplify the radical expression. And when do answers require absolute value? Basically when you have an even root and the answer that came out, okay, answers can potentially be negative, aka odd power. You'll see what I mean in just a second if you're still confused. Square root, even root, gotta watch out, of 16 is 4. Square root of 8, x to the 8th though, what times itself is x to the 8th? Well, what's x to the 4th times x to the 4th? That's x to the 8th. So the answer is x to the 4th. I don't need absolute values because this can never be negative. 4 is positive, x to the 4th, no matter what I plug in, will always be positive, if not 0. Okay? Another way to look at it is there's a little 2 here. What we like to do is divide your variable's power right here by the index. 8 divided by 2 is 4, and that gives us that. Cube root, you'll never need absolute values. So cube root of a to the 6, let's do our new trick, divide. 6 divided by 3 is a to the 2. 9 divided by 3 is b to the 3. Done. That's it. Fourth root, 8 divided by 4, 2. 12 divided by 4, 3. But guess what? I need absolute values on the y to the third because it has an odd exponent. If I fill in a negative number for y is a variable. It can vary, you can plug in different things. If you plug in a negative number for y, and you raise it to the third, it's going to be negative. So then we're saying our answer is negative to a fourth root, and that's not okay. So you need absolute value bars to kind of protect it over there, okay? Here, fifth root, won't need absolute values. Now let's divide. What's 16 divided by 5? We're going to divide like a fourth grader right now. How many times 5 go into 16? 3 times a to the third. But what's the remainder? That's what remains inside. That's a to the first. It remains inside. 17 divided by 5 is b to the, goes in 3 times as well, b to the third, but the remainder is 2, so it'll be b squared. If you want to put a little 1 for yourself, you put a little 1, really not necessary. Make sure you're putting the index really deep into that hook right there because you don't want it to spill out and turn into a coefficient. Square root of 81, we got 9. Square root of x to the fourth, 4 divided by 2, so it's x squared. Y to the sixth, square root is y to the third. Could anything be negative over there? This might. Let's make it safe. Another way to look at the just the variables right now. X to the fourth is 1, 2, 3, 4. And then y to the sixth is 1, 2, 3, 4, 5, 6. Again, the horizontal length matters. What's the square root of x squared? X. What's the square root of x squared? X. What's the square root, going a little crazy, of y squared? Y squared and y squared. So the answer to that, x came out. Answer to that, x came out. That's the x squared. And then these, there was a y for each of them. And that's how y came out. Is it a little babyish? Absolutely. But that's all we can do. All right, cube root of 169. You might be tempted to say 13, but it's 13 times 13. Do I have 3 of them? No. 13 is prime. I can't do anything else, so just stays inside. 12 divided by 3 is 4, so it's negative a to the fourth. 15 divided by 3 is 5, so it's b to the 5. 18 divided by 3 is 6, so it's c to the sixth. That negative could just sit out front, really doesn't matter. And there's the 169. Fourth root of 16, 2. The fourth root of x to the 12th is x to the third. Odd power, watch out. Y to the fourth. Z to the third, I can't really do anything with that because I don't have enough to make a group of 4. So there's my 4, don't lose your index. And then I need absolute value bars right there. Square root of 196 is 14. And square root of x squared is x. Square root, even root, absolute value bars are necessary. All right, so those were a bunch of examples for us right over there.